Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenter, Keisuke Saito.
Hi, everyone.
All right, thank you all for attending Rigaku's webinar. This is the fourth and final episode of our Practical XRD with Confidence series, and today we'll be exploring nanostructure with SAXS, WAXS, and X-ray reflectivity. So please note, if you missed any of the previous webinars, you can view them on the Rigaku website. This is going to be an interactive session, and I'll be posting relevant links in the chat window. We'll be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. Please submit those questions via the Q&A button at the bottom of your screen, and we won't be monitoring the raised hand function. Now, we'll try to answer as many questions as we can during the webinar, and we'll respond to any unanswered questions after the session is complete. If, for whatever reason, you have difficulty viewing the webinar live, please note that it is being recorded and you will be able to view the recording beginning tomorrow. And with that said, I'll turn it over to Keisuke.
All right, thank you, Tom. So welcome to the last episode. So we discussed X-ray diffraction last time. So today I'm going to discuss X-ray scattering technologies, including small angle X-ray scattering, wide angle X-ray scattering. So let me start from the fundamentals. So then I'm going to discuss the instrument setup and sample preps. So then I have two examples today on the oriented polymers and the Mesoporous silica. This is an isotropic case. So I'm going to switch over to X-ray reflectivity, starting from fundamentals, and then we will discuss how we could do fitting with the model of the sample structure to extract the sample information. So let's get started. X-ray scattering fundamentals. So first, let me discuss what is SAXS, what is WAXS, and the SAXS, we measure a very low angle scattering information in this red area. So what we see is like a nanoparticle's shape and the size and the distribution. So this is SAXS. While WAXS, so we move to the higher scattering angle. And as you may know, through the X-ray diffraction webinars, so we determine the crystal structures from the WAXS information. So there is no clear border between the SAXS and the WAXS area, but in general, so the border is around 5 degrees in the 2 theta, or 3.5 nanometer inverse in the Q scale, or 18 angstrom in the D space. So this table is summarizing a comparison between the different scattering and the diffraction technologies. So the first was the SAXS. So we target around 1 to 1,000 nanometer of the particle and the pores and the aggregates, as I mentioned. So you may be able to determine size and the shape and the distributions. And SAXS scattering is caused by electron density fluctuations in your sample. So WAXS, so we see more smaller, like a 0.1 nanometer up to 10 nanometer scale. So this is caused by atomic correlations. So you could determine like a crystal structure or phase information, the crystallinity, or local orders. X-ray diffraction, so 0.1 nanometer up to 1 nanometer scale, it's caused by Bragg diffraction. And as we know, we determine the crystal structure and the phase. And reflectivity is a little different. So we measure somewhere between 0.1 up to 1,000 nanometer scale. So it's caused by reflection from the interfaces of your thin film sample. So we could determine the thickness, density, and the roughness.
Okay, so I'm going to launch our first polling question here, and this is actually just to get a feel for who has joined us. So the question is, who has previously performed SAXS, WAXS, X-ray diffraction, or X-ray reflectivity? This is a multiple choice, so please click everything that you have done. Let's give Keisuke and myself an idea of who's joining us today. Keisuke, everybody's done diffraction at minimum.
Yep, very good.
Not surprised.
Good.
Not surprising.
Not surprised. Yes, as expected.
Exactly. So, and actually the other ones that's really interesting, they're all showing up at roughly 20 to 30% for each of those as well, for the SAXS, the WAXS, reflectivity.
Would you like to share the result?
Yep, and I'm going to go ahead and end the poll here. About 3/4 of the group has has answered. And so as you can see, we've got about, again, roughly 100% have done diffraction. And then 30 for reflectivity, 25 for SAXS, and 20 for WAXS. So this is a good group, and so everybody obviously knows the diffraction part. So now we have a good space to go. Thank you.
Okay, very good. Thank you. All right, so then let me continue then. So SAXS fundamentals. So if you may remember last time, so we discussed X-ray diffraction for thin film. So then I discussed like a reciprocal space, and we introduced wave vector, which is small k, which was defined by 1 over lambda. So lambda is an X-ray wavelength. And also we defined scattering vector k, large K. And in the Q space or reciprocal space, the Bragg equation was written by this formula, which is 1 over d. So DHKL is interplanar spacing on the crystal. So HKL Miller indices. If the large K vector is equal to the small g HKL vector, which is a reciprocal lattice vector, so we observe a diffraction signal. And the important parameter is reciprocal spacing is 1 over d. However, for the SAXS, we multiply 2 pi to the k vector. So this is because we use Fourier transform convention small q. So that's the difference of the definition between X-ray diffraction, small angle, wide angle scattering. All right, so what is the scattering intensity on the SAXS? So let's think about isotropic case. So scattering intensity I, in terms of the scattering vector Q, proportional to N with PQ and SQ. So N is the number of the nanoparticles in your sample. The PQ is called form factor. SQ is called structure factor. So the PQ, the form factor, so determines the shape and the size of your nanoparticle, while SQ is determined by how they are arranged in your sample. So let me discuss PQ first. So assuming this is your nanoparticle, so with the diameter 2 times of the radius r, so X-ray from the left is scattered by your nanoparticle. The scattering amplitude, AQ, in the case of sphere particle, is represented by this formula. So density rho, volume V, and a very famous sine, cosine as a function here for the sphere nanoparticles. And to convert this AQ to the intensity observed, or form factor PQ, so we normalize averaged by A0, this is the forward scattering intensity. And then, so we get a very well-known formula for the sphere. So this is a form factor for sphere. But a different shape of the nanoparticles have different form factors. For example, rod, like a type number 1, or discs, type number 2, the cubes, or quad shell, like an egg. So every different shape and density distribution over the nanoparticle has different form factors. So paper I listed here very well summarizes the form factor difference in terms of the shape of the nanoparticles. So you may want to refer to them. What about structure factor SQ? The structure factor SQ is a function of NR, so which is a particle count density function, and R0 is average particle density. So NR is actually the radial distribution function, or RDF, in your sample system. So radial distribution function is we assume like a reference nanoparticle, and this shows so how much other nanoparticles are arranged at the distance r, like this function. So this is called RDF. However, so to calculate the RDF, so we have to know the arrangement of the nanoparticles, or we may need to calculate over many, many nanoparticles in your sample. So that's why we introduce a kind of approximation. So this Pirkus-Yevik PY model is applicable for isotropic case. So this model provides a physically realistic hard share approximation to the RDF or distribution function, allowing SQ and ultimately the SAXS profile to be calculated using a very few parameters only. So that's why we introduced this model. So what is a PY model? So first of all, we assume hard spheres, so which means nanoparticles are not overlapped. It's separated. So then particles are arranged with the short range orders. So in this PY model, so we have three parameters. So first of all, the sigma. So this is a hard sphere diameter. So assuming this is your nanoparticle, so diameter here is a sigma. And the DNN, so which is average center to center distance to the nearest neighbors. So for example, from this reference atom nanoparticle, so we have a nanoparticles around here. So the average density to the nearest neighbor, the distance is DNN here. Or eta, so this is a packing fraction or volume fraction occupied by the spheres. So then finally, so we get this kind of like distribution functions against the reciprocal space scattering vector Q star, which is corresponding to the DNN through this equation. So this is a PY model. Okay, so before going into analysis details, so let me discuss about the SAXS setup and the sample preparations. This is a XRD configurations, which is very similar to what we discussed in the last episode for thin film. So X-rays from here. So then divergent X-ray is converted to parallel beam here by parabolic mirror. So then incident slit limits the beam height, introduces sample, and X-ray transmit through the sample. So then through the anti-scattering slit and the receiving slit, the detector sitting here collects the scattered intensity. But the difference compared to the thin film diffraction is here. Anti-parasitic scattering slit must be equipped between the incident slit and the sample. So what is this? So parasitic scattering happens, especially at a low angle, so which is caused by optics, such as slits. And the data on the left is comparing between with and without this anti-parascattering slit. As you see here, so without the slit, the background or scattering by the optics are very, very high, and the scattering from your nanoparticles are hidden under the background. How about sample preparation? For SAXS, you may prepare your sample in capillary. So we recommend the one made from fused silica because this provides the lowest scattering background. Your sample form could be liquid or powder. So different diameters of the capillary are available. You can pick one of the diameters depending on the volume of your samples. The other sample preparation could be foil transmission. So where your sample is going to be placed between the two like foils, either mylar or carton. Sample form could be powder, liquid, or gel. But the most important thing is when you prepare the sample, so we need to pay attention to how much volume of your powders are used in the experiment. So to do that, so normally we try to see the transmittance T. So this is a ratio of the intensity with and without the sample in sample holder. So we try to adjust the concentration or volume of your sample so that the transmittance is going to be somewhere between 20% up to 80%. If it is too low, it's too dense, X-ray doesn't transmit. If it is too high, so the scattering is very small. All right, so then let me introduce how you could analyze your SAXS profile. I'm going to discuss 3 different approaches how to estimate your particle size from the SAXS profile. The first of all, the peak search. So assuming this is your SAXS profile, and as you see, so we see oscillations. So if you see oscillations, so this suggests your nanoparticle sizes are very uniform, so small distribution. So that's why you see oscillation. So to determine the particle size, so we try to find out the first bottom of the oscillation here. In the Q scale, in this example, we found this bottom was about 0.9 nanometer inverse. And if you remember, the form factor PQ for the sphere model, the equation was like this. And when the oscillation becomes smallest here, like at the first bottom, the numerator in this equation is going to be 0. So this condition gives us the Q times large R is going to be 4.493. So now we have the Q number here. So you can put the Q here. So then finally you get the radius or diameter of the nanoparticle as a 10 nanometer. So this is the quickest and easiest way to extract the particle size. The other way to extract the particle size is so-called Guinier plot. So if the Q satisfies this condition, like a Q times Rg smaller than 1, scattering intensity IQ is calculated by this formula. So this is a forward scattering intensity multiplied with exponential, the Q square Rg square over 3. So Rg here is called radius of gyration. So this equation tells us if you plot intensity in a log scale versus the Q squared, this is scattering vector squared. So the slope of the scattering proportional to the radius of the gyration squared over 3. So for example, this is scattering intensity, it's the same sample. So intensity scale log natured, vertical direction, and the horizontal direction Q squared. And real data like a red and the linear fitted data dotted line, the slope here was negative 5.46. So then the radius and the radius of gyration in the case of a sphere has a relationship like this, square root 5 over 3 times bigger in the real radius. So you multiply this factor to the obtained Rz, and Rg is obtained from the slope of this plot. So finally, we got 10.4 nanometers. After getting the number, so we need to make sure this condition is satisfied. So Q times of the radius of the gyration should be smaller than 1. So if you put the radius of gyration here, so the Q max was found 0.247 nanometer inverse, so which is actually here. So that's why I use a plot only up to 0.247. The last method is model and fitting. So means the software is going to simulate scattering profile based on the form factor and the structure factor. So this example, the gold nanoparticle, which has like a spherical, like a shape, in the matrix, which was a toluene. So then scattering intensity red and the simulated and the fitted profile based on the calculation, model calculation blue. So the model fitting compared to the previous, like this previously discussed 2 different methods, not only average diameter, but also you can get extra information like a size distribution. In this case, 70% of the distribution. And also, depending on the software you use, so you may be able to get a distribution function profile, like a red profile. So the horizontal direction diameter of the nanoparticle the vertical direction, like a probability. Or the blue profile, which is a cumulative, the distribution profile. For example, from the distribution profile, so we get mode diameter. So the mode diameter is a peak top here. So which was 2.6 nanometers, or D numbers. This is for cumulative distribution profile. So D10 means up to 10%, the particle size up to the D cumulative distribution 10%. So we found 1.4 nanometer in this case, D50 up to 50%, 4.6 nanometers, 90%, 10.8 nanometers. So as you see here, so by the model fitting, so you obtain extra additional information from the fitting. So let's discuss a couple of the examples today. The first example, oriented polymers. In the last episode, we discussed in the case of no textured materials, so you can scan any direction, then you get identical information because your sample shows the dimensional ring. However, if your sample has strong preferred orientation, so depending on which direction you scan, sometimes you see the peak, sometimes you don't see the peak. For the SAXS, because we don't know what kind of texture we may have, so simply we record the scattering intensity two-dimensionally like this. So to do so, we have a very special setup. So let me discuss the SAXS configuration first. So this is the SAXS configuration example. So X-ray from the left is collimated or converted to the parallel beam. Up to here, the same configuration as the thin film. So then X-ray transmit through the collimator to shape the beam very small. So then after that, so we have anti-parasitic scattering slit to suppress parasitic scattering from the collimators. So then your sample is placed here. So then scattered intensity is going through the vacuum path because the scattered intensity is very, very weak. So then finally recorded by detector, 2D detector here. So in this geometry, we cover like a 0.2 degree 2 theta up to 7 degree 2 theta, or angstrom range, or scattering vector range, like this. The vacuum path suppresses air scattering. So the data on the left is showing the comparison between with and without the vacuum path. The without, as you see, the air scattering is very huge. So this is the X-ray scattered by air, like oxygen, nitrogen atoms. To the WAXS, up to the sample, the configuration are very similar, but the difference compared to SAXS is we get the detector distance very, very short. So as you see in this photograph, so this is a detector, 2D detector, sitting right behind the sample. So that detector covers as wide scattering angle range as possible. So that's the difference. So then we cover somewhere between 6.5 degree 2 theta up to 35 2 theta scattering angle. In terms of the sample holders, so you may want to have a different variety of the sample holders. As you know, depending on your sample shape and how you prepare the sample, like a capillary or foil or like a kind of bulk. So different shape of the sample holders are available, like an open, like a shape. So this is for capillary or bulks, for fibers, for films. So you mount your sample to those sample holders. For example, so this is polymer fibers. So in this example, the white, like a small, like a fibers here. So those are the polymer fibers, and X-ray transmit through the polymer fibers. And then the scattered intensity was recorded two-dimensionally. So this is the WAXS, 2D WAXS, the profile. And as you see, the varying intensity distribution is not uniform. It's concentrated like a horizontal direction, so which suggests So this fiber sample has so-called fiber texture. So then if you integrate the scattered intensity along the Debye ring, so you get this kind of like a XRD profile. If you have XRD database, so you can determine the phase. In this case, we found the crystal in this example is polypropylene. So this is how you could determine your crystal phase. How about SAXS? The same sample. So this is SAXS. So we saw the two spots on the top and also on the bottom. So from the integrated profile, so we found the peak position was 0.055 in Q scale, scattering vector scale. From the simple equation there, so we found this corresponds to the 11.4 nanometer distance, which is the distance between the amorphous to amorphous area in the polymer. As you may know, the polymer is consisting of the amorphous part and the crystalline part. So the 11 nanometer corresponds to the size of the crystal, or let's say the distance between the amorphous regions. Next example is Mesoporous silica. As I mentioned briefly at the beginning, so this is an example of an isotropic case. So this Mesoporous silica was prepared on a flat substrate, and X-ray from here is scattered by the nanoparticles and recorded by 2D detector. So this is obtained 2D wax profile. So first of all, so we do peak search and we found many peaks, but it's aligned very beautifully like this, and you could index like this. So I just skipped the last L in the mirror indices because L is perpendicular from the screen in this example. So for example, 1, 0 something here, 2, 0 something, 2, 1 something. And those spots are from the arrangement of the mesopolar silica. If you calculate the distance between the spots, which was 1.2 nanometers inverse in the Q space, and from the same equation, so this distance corresponds to 5.2 nanometers. So this is a distance between the mesopolar silica in the real space. All right, so let me summarize my talk for the SAXS and WAXS. SAXS and WAXS provide complementary structural information across multiple lengths of the scale. SAXS profiles contain quantitative information on particle size, shape, and the size distribution, and interparticle spacing. And 2D SAXS and WAXS shows us an isotropy and orientation of your nanoparticles or nano-objects, which enables us to characterize of textured materials such as fibers, films, and polymers.
Okay, thanks, Keisuke. So we've had some questions come in, and actually, I'm going to merge 3 of these questions together, Keisuke, because they were actually all a little bit about software. So bear with me while I kind of frame it for you here.
Sure.
So the first question was, can I do SAXS if I have multiple form or structure factors, right? So it's kind of that multiple kind of setup. The next one is also related, is can SmartLab Studio 2 handle the reduction and fitting of SAXS profiles? And then the next question, and again, this is kind of all software, so I'm kind of pushing these all together, is can you only determine the particle size distribution in materials that are crystalline? And then the second part of that question was, would it be possible to determine the size distribution of voids rather than the particles? So these are all part of the material, all part of the data processing. So I kind of put them all into a single subject. So you can answer them individually. So the first one was multiple structure factors and form factors.
Yeah, very good, very good. Yeah, thank you. I hope I remember all the questions.
Yeah, we'll revisit.
Yeah, the form factors. Yes,
they're all related.
Okay, so it depends on our software, but in our case, so our software handles only one form factors, but you can define multiple different size and distribution, the functions for each, the different sizes. And what is the second question?
So I think the second one would be, can you determine the particle size distribution in materials that are not crystalline?
Mhm.
Or can
Okay,
you only
understood.
do it if it's crystalline? So,
Okay, understood.
yeah.
Very good. The scattering amplitude, right, is not related to the crystal structure. So that means for the SAXS, the crystal structure is not important. As long as density contrast exists, the scattering happens. So in conclusion, so your nanoparticle could be amorphous, could be crystalline.
Okay.
Yep.
Okay. And then the other part of that question was, can you model the voids instead of the particles, right?
Yeah, so as we discussed, so let me go back to the form factors. Yeah, so different shape and the form, right, has a different form factors. And as long as your software support, all right, so your structure, your form factor, so you may be able to analyze. So for example, our software, right, from Rigaku, so we do support like a rod and a disk and a core shell or particle or like a random fractal, like a gas or liquid could be. So those four are supported.
Okay. All
Yep.
right. Then the last one actually was, can SmartLab Studio 2 do the reduction and fitting of SAXS? And so I think that's where our MR SAXS module comes to play for that.
All right.
All
Thank you
right.
for choosing Rigaku, first of all.
Yeah, exactly.
Yeah, so data
Yeah.
reduction, yes, is possible. And for example, if you measure the SAXS, I didn't discuss, but before analyzing, the SAXS profile, so we need to subtract the background. So you measure empty sample holders and then measure the same SAXS data and you subtract. So this kind of data reduction treatment is done by MR SAXS. The smoothing knot, normally we don't apply smoothing a lot, but if you have to, so our data manager software can do smoothing on your data. So after that, you can transfer the data to the MR SAXS software to continue the analysis part.
Okay. Okay. Very good. So we'll move on to the polling question next, Keisuke. If you want to scroll forward, I'll go ahead and launch it. Okay. So the second question is, have you done 0D or 2D SAXS? And again, this is 0D, 2D, both, or I don't. So, okay. So this actually is this is simply clarifying the group that does do SAXS a little bit. And again, we did have a large group that didn't do SAXS at all, so we understand those. And it's coming in roughly of the ones that have answered is that they both do 0D, 2D, so good group here.
Understood.
So let's just go just a little bit longer. We've got about half of our answers in. And we'll give another 15 seconds here for any more answers.
Okay.
All right. So let's go ahead and end this poll here. We've had about half of our users answer. And so again, roughly 10% do 0D and 10% do both. About 15% do 2D, which actually I find that quite interesting. And again, we knew this kind of from our initial that there was a portion of our listeners today that don't do SAXS at all. So we appreciate you joining us too.
Yep.
All right.
Thank you, Tom, and
Thanks,
everybody.
we can move right along.
Yep. Very good. I hope I gave you a kind of good insight about the SAXS and WAXS so that you might be motivated to try.
Yeah.
All right. So let me continue. So next topic is totally different. So which is X-ray reflectivity. So let me start from fundamentals. So we have a different, thin films available right in our world. For example, semiconductors, magnetic films, optical coatings, or organic films, and biomembranes. Just a few examples here. But why do we care about the surface and the film? First of all, we may want to determine the film thickness, or we are wondering if interface is sharp or diffused, or how smooth is the surface. So to address those questions, so we have different technologies available, right? For example, atomic force microscopes only probes the top surface, as we know, or scanning electron microscopes, which requires the cross-section sample preparation, and also as this example showing, the resolution might not enough to resolve a very thin film thickness. How about transmission electron microscopes? So which is a destructive? So means your sample might be gone after the measurement. And also it's a labor intensive. A lot of labors are required. Even though the resolution might be much better than the SEM and might be sufficient to determine the thin film thickness. So compared to those, the X-ray reflectivity is a non-destructive, the characterization, so which shows us the film structures without destroying. So X-ray reflectivity measures as how X-rays are reflected from a surface as a function of incident angle. So that means we change the incident angle step by step, and we see how much X-rays are reflected from the surface and the interface. So which shows us the thickness information. So between 0.1 nanometer up to 1000 nanometer range, density, and the surface and the interface roughness. Somewhere between 0 to up to 3 nanometers. So the paper here is very famous. So this professor discussed what could be the maximum roughness we could determine by XRR. So he mentioned the Q, this is scattering vector along the Z, which means a scanning perpendicular direction in the reciprocal space. So QZ maximum multiplied with the sigma, this is a roughness maximum, should be well larger than 1. So this condition gives us approximately the 3 nanometers maximum roughness you could evaluate by XRR. So this is a typical XRR spectra. So first of all, as I briefly mentioned, so we scan perpendicular direction in the reciprocal space, which is called the specular refraction. So scattering vector Q perpendicular from the sample surface. So from this data, as you see here, up to this angle, X-rays are pretty much almost 100% are reflected. But after this angle, X-ray starts penetrating into the sample. So this angle is specifically called the critical angle for total refraction. So this angle is a function of the surface density. And then, so you may be able to see the thickness oscillation like this. So this gives us the thickness information. And the amplitude of the oscillation provides us density information. And the slope gives us surface roughness information. So very briefly, so we can extract those information from the XRR spectra. Instrument configurations for XRR. So this is exactly the same configuration as the one used for thin film characterization. So parabeam hit the sample, reflected X-rays are recorded by detector here. So parabolic mirror has a divergence about 0.02 degrees, which determines the maximum thickness to be measured, which is around 220 nanometers. If this is too thin for your sample, so you may want to put germanium monochromator here after the parabolic mirror. It's the same story as the thin film. So then beam divergence is going to be half compared to the parabolic mirror. So this extends the maximum thickness to be measured up to 440 nanometers. So the oscillation space in the theta scale and the thickness T has this kind of relationship. And this provides us, if you put the maximum thickness can be measured by X-ray divergence on your system. And so you can plot like this way. So this gives us an information or idea. So what could be the maximum thickness you could determine depending on your instrument configuration, if you know the instrumental function. So the delta theta instrument means instrumental resolution, like a divergence of the X-ray. For example, parabolic mirrors, 0.02 degree, as I mentioned. So it gives us like a roughly 200 nanometer plus minus maximum thickness. G germanium 4002 bounce, 440 nanometer. We do have 4 bounce monochromator 2, germanium 224 bounce, which may be able to determine over 1000 nanometer thick in theory. So then how we can calculate or we determine the reflectance on the thin film structure. So first of all, if the incident angle theta is smaller than the theta c, X-ray is reflected almost 100%, as I mentioned. When the theta equals to theta c, most of the X-rays are reflected, but some of the X-rays now propagating parallel to the sample surface. So then after the theta c, so X-rays penetrates into the sample. And X-ray is refracted as well. So the penetration of the X-ray or reflectance is a function of refractive index. So refractive index of the material for X-ray wavelength region is presented by n equals to 1 minus delta plus I beta. So delta is calculated by this and the beta like this. So this term is almost like a constant. And the delta is a function of z and f1 prime, and the beta is a function of f double prime. So z is the number of the electrons of atoms, so which means density. And f small f's, so those are real and imaginary part of the anomalous dispersion, which means absorption factor. So that's why, in roughly speaking, the delta is a function of density and the beta is a function of absorption of the material. And then critical angle for total refraction, theta c is calculated by square root 2 times of the delta. So that's why I mentioned the theta c is a function of density of the material. All right, so then this is how we calculate reflectivity from the multi-layer stack. So we use so-called Parrott's recursive the formula. So this presents the reflectivity R at the interface between nth and n minus first layer. So reflectance at this interface is calculated by small a, large R, and large F multiplied with exponential term, so which is a function of the sigma, and the Bragg angle theta and X-ray energy lambda. And small a here is a function of the thickness, and the large f is a function of small f, which is a function of delta density, and the roughness term is here. So this is the reason why we can determine the thickness, roughness, and density from XRR profile fitting. So this is the definition of the roughness. So we use so-called Nieffert cross roughness model. So those professors defined electron density profile at the interface is presented by error function. So assuming this is a thickness direction, this is the density of the materials, and from the row 1, so this is the interface. After the interface, density increased up to row 2. So then blue profile, this is the error function following this formula. And then they introduce sigma here, so which corresponds to the standard deviation of the Gaussian, which is the first derivative of the density profile. As you may know, the first derivative of the error function is a Gaussian. So this is a d rho over dz. So this is a Gauss function profile at this interface. So they define the roughness as a standard deviation of this Gauss function, the sigma here. Okay, what about penetration? So how deeply X-ray penetrates? So penetration depth d around the critical angle for total refraction is calculated by large d here. So large d is a function of large b, and b is calculated by this, which is a function of delta and also beta, so density absorption function. So if I calculate this for the silicon, so which is a green profile here, the first of all, the theta c was calculated as 0.22. So this is 0.22 degree critical angle. What about the red is for molybdenum? So density higher than silicon, which is 10.3. Platinum even higher, almost like a 21.5. So as you see, so as density goes up, the theta C also going to higher and higher. And most importantly, if you have a look how deeply X-ray penetrates, around the theta C, the penetration of X-ray is very limited to the topmost surface area, a couple of nanometers from the sample surface.
Okay, so we're going to go to a few questions here. Keisuke, we've had actually some really nice questions come in. So I'm going to focus on two of them, and then you can finish up. So the first question is X-ray reflectivity comparable to specular ellipsometry? And are there pros to reflectivity compared to ellipsometry? And I kind of brought that up because you mentioned specular ellipsometry at the very beginning and with the scattering factor.
Okay, very good. Thank you. Thank you. So I'm not, to be honest, not a specialist for ellipsometry, but basically, so if you have a dual, like a two different laser, the wavelength ellipsometry system, so most probably ellipsometry should be able to determine the thickness C's or your multi-layer just stack like a XRR does. But if you have a single wavelength refractometry, like a ellipsometry, I'm not sure 100%. So you may be able to have a double, like a two lasers to determine the thickness density information like a XRR does. I could be wrong. I apologize.
No, that's okay. That's a tough question. I thought it was worth addressing just to do that. And then the second one that I wanted to ask here is, does the shape of the X-ray beams, line versus point, affect the results of SAXS and X-ray reflectivity? So kind of both of them, right?
Yes, definitely. So the X-ray, the shape, or let's say the intensity distribution across the direct beam is very important for SAXS, and this is convoluted. This needs to be convoluted in the simulation. So I skipped this part, but if you remember on the possibility number 3, how to determine the particle size based on the modeling and the simulation. So we have a very important step to convolute the intensity profile of the direct beam into the calculation. Yeah, thank you for the question. XRR, yes. So the X-ray beam as a footprint on the sample surface is kind of very important. So I'm going to discuss later, but this needs to be corrected in the simulation as well.
Okay. All right, let's move on to our final poll question here. And this one's actually fairly simple. Is have you previously considered reflectivity?
Yep.
Oh, there we go. Reflectivity modeling to be nanostructural analysis. I never thought of it. I always think of it as density, smoothness, roughness. And so, but when you think about what it really is, it is nanostructures and these nano, so actually interesting here, Keisuke. So of the group that's answered, 3/4 had never really thought of it that way. And so I kind of suspected that because I never thought of it that way myself.
Okay.
So we're at about 50% here. I'm going to go ahead and end so that we have enough time for you to finish. So let me share that again. And so as you can see, of roughly 50% that answered, 3/4 hadn't really considered it nanostructural analysis. So all right.
Very good.
Thank you. Let's go ahead and we'll finish up, and we have some extra questions at the end.
Yep. Thank you, everybody, and Tom. All right. So let me discuss the last part of this episode, so which is XRR modeling and fitting. But before going to fitting details, so let me discuss a little bit more about the fundamentals of the reflectivity, because this is kind of important for you to know before analyzing anything using the software. So first of all, the thickness. This model, this is simulation, by the way, on the silicon dioxide, only 5 nanometer thick on the gallium arsenide, the substrate. So I changed the density of the silicon dioxide layer from 1 to 2.5. And I remember I mentioned the critical angle here, theta C, corresponds to the density of the topmost layer, in this case, silicon dioxide. But even though I changed the density, this simulation shows the theta C the same between the different densities. The question is why? So the critical angle total refraction only represent the density of the topmost surface layer if the thickness is thick enough. So obviously the 5 nanometer thick silicon dioxide is too thin to show the theta C. So this is something we need to be a little careful when you analyze the data. So this is a similar example, but I simulated wider scattering angle range up to 10 degree to theta. The same structure, 5 nanometer thick silicon dioxide, but I fixed the roughness to 0.3 nanometers. I changed the density like this, and you see, so the amplitude of the fringe changes depending on density. So if you want to determine the density of silicon dioxide, so this is going to be the alternative way. So how you could determine the density. So which means not from the critical angle total refraction, but you could use the simulation fitting and fit the amplitude of the fringe to extract the density information. How about roughness? So now I fixed the density to 2.2, but I changed the roughness sigma from 0.3 up to 2.0. So sigma changes maximum to theta angle to observe the fringes. For example, 0.3, so we see fringe up to 10 degree to theta, while 1 degree, maybe up to 4 degree here. So 1 nanometer up to 4 degrees, or 2 nanometer surface roughness only up to maybe 2 degrees to theta. So then let's discuss how we could fit the model. All right, so this example, the raw data in the black is an XRR profile from this structure on the right-hand side. The first of all, silicon substrate. On top of that, so we had nickel iron with the 16 nanometer thickness, and tantalum on top of that, another 16 nanometer thick, and finally tantalum oxide, 2.3 nanometers. Density like this, roughness was fixed to 0.5 at the beginning. All right, so now the simulation blue is not really matched to the data. The first thing I would do is to pay attention to the scale. The scale in the simulation is a little too high. The blue is a little higher than the raw data. So this is something you could adjust by yourself manually. And next is the background. So the background, this is a light blue line, straight line here. So this is the assumed background, so which is a little too high compared to the raw data. I normally adjust those two parameters manually because those are easy to be identified. So after the fitting, so this is what I got. So next is the theta C here. As we discussed, from the theta C, so we should be able to determine the density of the surface layer. However, as we discussed, 2.3 nanometer thick tantalum is too thin to get the critical angle total refraction. So basically, do this theta C show the density for the underlying the tantalum layer, which had 16 nanometer thick. And from the fitting, so we found the density of the tantalum was 15.7. So those parameters are refined and fitted even manually. So because we can see by our eyes. I normally do this fitting manually at the beginning before starting automated fitting procedure. After that, I normally let the software fit all the spectra, all the patterns, and overall fitting has been done. As you see, the simulated profile well matched to the experimental data. So then you get red parameters in this table. So this is how you could overall fit the XRR data. But of course, in most of the cases, the fitting doesn't go such a simple way. So that's why at the end of this episode, so I wanted to discuss with you so how you could improve or how you could make the fitting procedure easier for you. So first of all, if you have TM in your campus, in your company, so maybe try TM to get some idea about the thickness. As we discussed briefly, the TM may be able to show you the thickness information, and you can use those numbers from TM as a starting numbers in the XRR fitting. The other possibility is to prepare as large sample as possible. So this is related to one of the questions in the Q&A session. This is because X-ray reflectivity eliminates a very, very large area on the sample surface. So the simulation on the right-hand side is showing, depending on, is showing the XRR profile depending on the size of the surface of the sample. For example, 5 by 5 millimeter square or 10 by 10, 25, 25. And as you see, a red circle highlighted area. So smaller sample size, the intensity is going down compared to the bigger sample. This is because X-ray footprint is bigger than your sample surface. So if so, when you simulate and fit, so you need to correct the intensity. Otherwise, the reflectivity never fits. Some software has this kind of correction feature, but some software does not have the feature. So if your sample is very small, so you may want to have a software which has this kind of correction features. All right, last three. So this is my personal advice. So characterize individual layers step by step instead of building complete stack of the film from the beginning. So what I meant is like this. So if you have more than one layer in your stack, so first let's stop after the first layer deposition. So then you can determine thickness T1 and the roughness to the substrate interface, sigma 1 by the XRR. So then you deposit one more layer on the top, which is the T2 and the sigma 2, roughness thickness. And then when you fit the step number 2, so you could fix the T1 and the sigma 1 in a parameter set so that you can only refine T2 and the sigma 2. So this makes fitting much easier compared to 4 parameters because you only got 2 parameters to fit. So then if you have more than 2, so you can step by step figure out the thickness, roughness, the thickness, roughness. So then finally, so you should be able to fit to the complete the sample stack. Okay. All right, so let me summarize my talk for XRR part. So as we learned, so XRR is a non-destructive technique for characterizing thin films and interfaces and providing thickness, density, and the surface interface roughness with the nanometer scale sensitivity. Instrument configuration determines the measurable thickness range extending from a few nanometers to over 1 micrometer with high resolution setup. Thank you for your attention.
All right. Thank you, Keisuke. So we do have just about a couple of minutes left here. So I'm going to try and get a couple of questions in. I think we had a couple of nice ones come in, Keisuke. So the first one is in the context of film thickness measurement, can you also comment on Lowy observations that are observable in regular XRD?
Yes, very good. Yeah, so Lowy diffraction oscillation, the XRL or thickness oscillation, the same information. And we discussed in the last episode, so you can do either dynamical calculation, simulation fitting to extract the thickness from the diffraction experiment or from the peak search like we do for XRL. So either way, so provides the same information.
Okay.
Thank you for the question.
All right. And the next one is, and I think this one's a nice one as well, is can XRR be used to measure the thickness of an amorphous polymer coating deposited on an amorphous substrate?
Very good. Yeah. So XRR like a SAXS, right? So this episode I focused on the scattering. So scattering means, we don't have to have the crystal structure. So means amorphous, the crystalline thin film, either way is fine. So, but we need to have a contrast of the density between the layers. So it means if your polymer has enough density difference compared to the substrate, so your thin film should show the reflectivity profile. But if the substrate, your layer, has similar density, so from X-rays viewpoint, the interface is not clear because of the similar density. In such a case, you may not be able to see beautiful like a thickness oscillations because of the lack of the density contrast. I hope I answered to your question.
All right. Thank you, KSK. All right. So in the interest of time, that's all the time we can do on questions. And for those that haven't answered, and there are some very good ones, we'll respond to those directly. So again, as I said earlier, a recording of the webinar will be available tomorrow, and an email will go out to all registrants with instructions on how to view the recorded presentation. Thank you all for joining us, and we look forward to seeing you at our future webinars. Thank you all.
Thank you. Bye-bye.
Bye.